So in the last class we essentially convinced ourselves that only with linear and time invariant networks we can't get any power amplification. So what kind of devices we need? We need nonlinear devices, and we started with the one port nonlinear network. We essentially saw that if this one port nonlinear network should act like an amplifier, its nonlinear characteristics should have a positive slope or a negative slope. And the nonlinear device alone is not sufficient to give the amplification. It needs to be powered by something. And what is that something? DC source, and that's what we call DC biasing. And the voltage and the current at which the nonlinear device is operating is what we call the operating point. So then we looked at how to analyze such nonlinear circuits. So in general, if you are given something like this which has both DC and small signals that need to be amplified, the idea is the following. You first solve for the operating point, that is, you assume that compared to the DC source, the signal that you are trying to amplify is so small that you can sort of make it zero, because first you have to find out in which operating region the nonlinear device is operating, because as you see this has multiple operating regions, and that's what you do first. So you first solve for this, solve for the DC operating point. You make all the small signal sources zero, and then you solve for the nonlinear equation and get the operating point, and then you go on to find the effect due to the other small signal input. So once again, with the addition of this additional voltage source V in, strictly speaking, you again have to solve a nonlinear equation. But we just saw that as long as the voltage changes we are looking at are so small, and by small, it should be smaller than this quantity. If so, the nonlinear characteristics can be approximated as a linear characteristic. And here I have a one port nonlinear device. So the voltage and the current are related in a nonlinear fashion. But for small signals, the changes in the voltages and the changes in the current, they will be related in a linear fashion. So which means for small signals, how can I model this as a resistor? Something where the voltage and current is linearly proportional, it's a resistor. So that's what you do. So essentially for small signals, you first draw the small signal equivalent circuit. That is, you replace every component by its small signal equivalent. And as we just saw, if I have a one port nonlinear network, for small signals, I can think of it as a resistor. And the resistor's value we computed, it's the inverse of the slope. And the slope must be evaluated at the operating point. Okay, that's the most important thing. Similarly, if I have a DC voltage source, what do? You short circuit it, because we are looking at small signals, which means we are looking at changes in the voltages. So if I have a DC voltage source, the voltage is not changing, so which means there is zero change, so you make it as zero. Similarly, if I have a DC current source, the current is made zero, so it's like an open circuit. So that's what you do. You replace all the elements with its small signal equivalent circuit. If you have linear elements, it's trivial. For nonlinear circuits, you have to find the small signal equivalent, and then you solve for the small signal voltage. So the total signal will be the operating point you computed plus the small signal you computed. But then we proceeded with the two port nonlinear network, because with the one port, the amplified signal was available across the device itself, but we want this to be available across some load resistor. So we moved to a 3-terminal 2-port nonlinear network. So again, this has a nonlinear relation, and we wanted to find out how should this nonlinear relation look like so that we get power amplification. So once again, we took this nonlinear equation, we sort of expanded using Taylor series. Assuming signals are sufficiently small, we ignored the higher order terms, so that gave us only this linear equation, which means for small signals I can model this nonlinear network according to this equation, and that turned out to be this. So for any nonlinear 2-port network, for small signals, we can model it using the 4 Y parameters. So the equivalent circuit is essentially this fellow. It's basically a voltage controlled current source in parallel with the resistor, both at port 1 and at the second port 2. Right? So, but then we later argued that if this has to behave like a good amplifier, we noticed Y11, Y12 Y22 all have to be 0, so, and we should have a large Y2. So which means if I take a good two-port nonlinear network, if it has to be a good amplifier, for small signals it should essentially behave like a voltage controlled current source. That's all it matters. Okay. So now from the understanding we had on the small signal Y parameters, we try to sketch the nonlinear characteristics. So we know that Y22 0 for small signals. Y22 essentially is relating second port current with the second port voltage. So which means if I sketch I2 versus V2, around for small signals in a range of voltages, the slope is going to be 0. So that's what we got, a 0 slope, and the actual characteristics looks like this. Same is the case for Y21. Y21 is very large, so the slope is going to be large in a range of voltages, and the actual characteristic should actually do this. And as you guys recognized, MOSFET is one device which has this kind of an IV characteristic. So we'll start looking at MOSFET now. So again, to summarize what we saw, let me rewrite it again. So this is my small signal voltage. So let's say this is Vin and Rs. If I give it to a two-port nonlinear network, say this is RL. So let's say this is port 1, port 2. So let's say this is V1 and V2. We essentially saw if this has to be a good amplifier, only Y21 has to be non-zero and that has to be large. All the others have to be 0. So the small signal equivalent looked like this. Just had one voltage controlled current source. This is port 1, port 2. This is Y21 times V1. Right? And we also saw the characteristics look like this. If I sketch I2 versus V2, we wanted small signal Y22 to be 0, so which means the slope is 0 here, and then it sort of does this. Similarly, if I sketch I2 versus V1, the slope has to be large, so it basically does something. And it turns out for a MOSFET, the current at the input side is 0, so Y11, Y12 are automatically made 0. That's because my input current for MOSFET is exactly 0. And as I mentioned, remember that it is not just MOSFET. Any nonlinear device which has small signal Y parameters of this form, wherein you have large Y21, all the other Y parameters to be really, really small, any device like that can be used to make amplifier. And it turns out all transistors in general satisfy this property. So now let's try to replace this with a MOSFET. So let me see if I can copy this. So I just will replace this fellow with a MOSFET. Again, remember what we are drawing is only the small signal equivalent circuit. In practice, the MOSFET also needs to be biased so that it is operating in whatever operating region you want. Okay. And sure you guys remember this is called the gate, drain and source, right? So which means the port voltage V1, it is essentially the voltage across gate and source. Similarly, port voltage V2 is what? It is VDS. So which means the characteristics here I have V2, I'll replace it with VDS, and the current at the second terminal, what is that current in a MOSFET? I2 is what here? ID, the drain current. So hopefully you guys remember. So same thing, this is drain current, V1 is VGS. So for MOSFET also the small signal is going to look like this. So So which means terminal 1 or port 1 is essentially your gate, port 2 is essentially your drain, and the terminal common here is source. Okay, and recollect, small signal Y21 is essentially the derivative of the second current with respect to the first port voltage. I2 versus V1 is Y21, right? And this you evaluate at the operating point. For MOS current, this essentially is derivative of ID with respect to what voltage? VGS, and evaluated at the operating point. And for transistors, we call this to be the trans conductance GM. Of course, conductance because it's current by voltage, trans conductance because you are looking at current in one port, how it varies to voltage in another port. So now we can replace the small signal here. So V1 is basically VGS, so I'll change it to be VGS. Similarly, Y21 is essentially GM, V1 is VGS, so I'll replace this to be GM times VGS. So let's actually apply the input source and see what happens. So this is my small signal input, this is my RL, right? Basically I have drawn the small signal equivalent of this circuit. Is that okay? The transistor I am replacing it with its equivalent linear model, and the rest is the same, V in and RL. Is that okay? So now tell me, if I apply V in here, what is the small signal VGS? V in, is that clear? So which means what is the current flowing down? GM times VGS, which is GM times V in. What is the current flowing up? Minus GM V in. So what is the output voltage you get, small signal? Yeah, so minus GM times RL times V. So the small signal gain is essentially minus GM RL. Okay. And again, what we have drawn is only the small signal equivalent circuit, the linearized small signal picture. But in practice, you have to bias the transistor so that the nonlinear device is operating in your required operating region. So before we look at biasing, let's try to understand some things on MOSFET. Again, I will not go into the how MOSFET is constructed, it's fabricated, how it charge carriers flow here and there. That's not the focus of the course. Instead, over the next 30-40 minutes, I'll try to give you some explanation as to, as a circuit designer, what are the basic things you need to know about MOSFET. That's all. Nothing about semiconductor devices. That's not the focus here. So let's move on. Let me see if I can copy paste this. Erase all this. Okay. So maybe I'll have this characteristic. Let me have the MOSFET symbol and the equivalent circuit. Oops. Great. So now, of course, we know we have to bias the transistor in an operating region. Now, if I give you this kind of an IV characteristic for this nonlinear device, in which region would you want to bias the device in? I mean, this is the characteristic, right? Here, where would you want to bias it in? In the flat region or in this region? Why? Huh? What is constant? Yeah. This is I2 versus V2. What we are talking about? No, I mean, I have written also, right? Look at this. For a good nonlinear for a good amplifier, what small signal parameters you should have? Everything should be 0 except Y21. So here, which Y parameter I can get information about? Y? 21 or 22 or 12? Y22. I mean, I am looking at second voltage, and I also written it. Man. You want Y22 to be 0, so the slope has to be. Slope must be 0, or the curve should be constant. So you want to bias somewhere here. So which means I can basically, let us say, demarcate this into two, let us say, regions. One where the slope is very small, other where the slope is large. So of course you guys know this is called the saturation region. This is linear region for obvious reasons. So let's try to understand the IV relation in both the regions. So let's start with linear region. So it turns out if the transistor is in linear region, this is the condition. The gate to source voltage, the operating point gate to source voltage must be greater than some voltage called threshold voltage. Again, why threshold voltage comes about, I don't know. I will not explain in this course, because in this course you don't have to worry about it. And in addition, the operating point drain to source voltage is less than VGS minus VTH. So hopefully you might have seen this somewhere. And the current expression is this mu n C OX W by L. So VGS minus VTH times VDS minus VDS square by 2. So here hopefully you guys know mu n is the mobility of charge carriers, Cox is the capacitance, W is the width, this is the length. Okay. Now these parameters mu n Cox VTH, they are all sort of constants. So as designers you don't have control over them. So as designers the only things that you can control are the width of the transistor, length of the transistor, the operating point VGS and the VDS. The ones I have marked in green dots are the only things that you can control as a designer of a transistor. Now it turns out, again you might have seen this already, if I am looking at a really small VDS, that is if VDS is much smaller than VGS minus VTH, I have two terms here. Which term will dominate if VDS is very small? First term will dominate. VDS is really small, so VDS square is going to be much smaller. So then ID is mu n Cox W by L times VGS minus VTH times VDS. So now you tell me if here the drain voltage and the the drain current and the drain to source voltage, they are related in a linear fashion or a non-linear fashion. Does it make sense from the characteristic? Yeah, of course. For small VDS, sort of linear. Great. But of course, this is not where you want to bias your transistor. You want to bias a transistor somewhere where Y22 is 0. So that's the saturation. And for saturation, the condition is again VGS must be greater than the threshold voltage, and the operating point drain to source voltage must be greater than VGS minus VTH. And the drain current has this relation half mu n Cox W by L times VGS minus VTH square. So from this equation, if I increase VDS, is my drain current changing? No. Does it make sense? From the characteristic, does it make sense? That's what you want, right? You want the slope to be 0. which means if I increase VDS, I don't want anything to happen to my drain current. That's what I mean by small signal Y22 to be 0. But of course, you guys already know this is not completely true. In practice, there is a small dependency on VDS. So which means Y22 is not exactly 0, but it is sufficiently small number. And this is modeled with inclusion of this term to 1 plus lambda VDS. Again, hopefully this all this is all looking like a recap to you, not the first time you are encountering. Even if it's the first time, no problem. Okay, so now with the addition of this term, my small signal equivalent circuit, how will it change? Will it change or it will not change at all?
Sir, I think there should be 1 plus lambda into delta VDS.
What is delta VDS?
So VDS minus VDS minus VDS.
It's just VDS.
Okay.
That's all taken into account in the lambda term. The actual expression is this. Okay. So this is the now we know that Y22 is not 0 exactly. So how will this change? This, because remember we just saw that I take any nonlinear two-port network. For small signals, it's going to look like this with all 4 Y parameters. For a MOSFET, incidentally, the gate current is 0, so Y11, Y12 becomes 0. So which means I'll have both Y21 and Y22. So which means I'll model this using a resistor in parallel. We'll call the conductance to be GDS because the conductance between drain and source. And how do you get GDS? Remember, GDS is essentially your Y22. So how do you compute this now? I mean, Y21 or GM I computed by taking the derivative of ID with respect to VGS. This is Y22. So how will I do this now? Derivative of what with what? ID with? Okay. Again, compute at the operating point. So of course, the inverse of this is the resistance RDS, or sometimes we say it to be R0, and I'll use R0 because if I write this in subscript I have to write 2 characters, but here I can write 1 character. Great. So which means in my actual amplifier here I am going to have an additional resistance, which is I'll call it R0, correct? So now how will the gain change here? Again, we can look at this from start. I am applying a V in. My VGS is going to be V in. The current flowing up is how much? Minus GMV in. That is flowing through a parallel combination of that's all. So this just becomes minus GM into RL parallel R. Okay. Great. So which means sometimes we often do this. So let us say I apply the small signal input directly at the gate, okay, and I try to measure what is the small signal drain to source voltage V out. How much will that be now? I am applying V in directly at the gate to source, and without any load connected I am trying to measure what is the small signal output. How much is that? Minus GM? Minus GM R0. What is VGS? VGS is same as V in. So again the current flowing up is minus GM V in times R0. So let me erase this. So the gain we have is minus GM times R0, right, or minus GM by GDS, whichever way you want to see. And this is what we call the intrinsic gain. This is the gain without any load being connected to the transistor. In a way, that's a maximum gain you can have. Is okay? Great. So now a question to you. So this notion of modeling a transistor as a voltage controlled current source in parallel with a resistor, you think this modeling is valid for both linear and saturation region or only in saturation region? Huh? Only in saturation? Why not? What did linear region do to you? Again, it's a nice interview question to ask. Huh? Sorry? Yeah, but the model, do you think it's valid or not? Huh? I mean, please remember, we just saw, right? Any nonlinear two-port network, for small signals, I can always model it like this. This is essentially a voltage controlled current source in parallel to a resistor at both the ports. For a MOSFET, yeah, of course, this guy is 0. So which means, irrespective of where I am operating the transistor in, I can always model it as a voltage controlled current source in parallel with a resistor at the drain side. Is that clear? Now, depending on the operating region, what will change? Yeah, the values of y21, y22 will change. Because remember, these are the slopes computed at the operating point. The values of the y parameters will change, but the model is still valid. Okay. So again, this is a common mistake students try to make. It's a nice interview question to ask. That people always think it is valid only in saturation, but that's not the case. This is a nonlinear device. I don't care where it is operating. For any small signal change, I can always model it this way. So which means this model I have, maybe I will say, write it here, valid in all regions. Is that clear? Now, of course, as you guys pointed out, depending on the region, what will change here? Values of what? Yeah, for transistors, what parameters are they? GM and? Right, that's all. So let's compute those values in both linear and saturation. So let's first do GM. GM is essentially the derivative of current with respect to VGS. So I take, let us say, this equation, take the derivative with respect to VGS. What do I get? UNCOX W by L. That's all, into VDS. Right? Similarly, I can compute GDS. GDS is essentially the derivative of current with respect to VDS. I take this guy and take the derivative with VDS. What do I get? UNCOX W by L times. Is that okay? I'm just differentiating this equation with respect to VGS minus VTH to get this. The same equation I am taking the derivative with respect to VDS to get this. So which means I can now compute this intrinsic gain, or let's say I'll take the magnitude of the intrinsic gain. That is basically GM by GDS. Fine. I take the ratio of the two. What do I get? VDS upon is that okay? And if it is in linear region, VDS is smaller than this quantity or greater than this quantity? Smaller than VGS minus VTH. So how much is the intrinsic gain? Yeah. Of course, that's why you don't want to operate it there. So let's repeat the same for saturation. So again, I'll first start with GM. For GM, I have to differentiate this equation with respect to VGS. So I do this, which means I'll have UNCOX W by L times VGS minus VTH times you have this 1 plus lambda VDS also. But for typical, for most of these calculations, we sort of assume that this slope is very small that we can sort of ignore. Basically, this equation is not exact, it's approximate. and the approximation is okay because to start with this equation itself is already approximate. To make our life simple, we'll sort of ignore this for operating point calculations. Okay, so now of course from this equation you can find what is VGS minus VTH in terms of ID. Then you can replace it, so then you will get another expression for GM, square root of 2 ID times by L. So basically what I have done is I find what is VGS minus VTH in terms of the current ID and I replace it here. It's just algebra, I don't want to do these calculations here. And what is the other expression you know for GM, if you already know? I mean, I have mu and COX W by L into VGS minus VTH. I take, let us say, this equation. I divide both sides by VGS minus VTH. Then one power goes off. Then it's essentially similar to this. So this is basically 2 times ID. I mean, this should be trivial to see. I multiply this by 2, so this half goes off. I divide by VGS minus VTH. I have square, so one power gets reduced, and of course I am ignoring this term. Now again another question to you, another good question. This was asked to my friend in his IMA or IMB interview somewhere. So if I look at this expression for GM, it seems like GM is directly proportional to width W. Whereas second equation, what it says, GM is proportional to square root of W. What is third equation saying? GM is independent of W. Oh, so what is true? Yeah, but let us say, I mean, if I ask you, is GM proportional to W, proportional to square root of W, or independent of W, what's your answer? Huh? Sorry? Proportional to W. But here you see it's inversely, I mean, proportional to square root of W, right? I mean, can I have a case where GM is proportional to square root of W? That's a question. No? It's a math question, man. Look at this. I'm saying GM. I'm looking at 2 variables now, ID and W. If I want to make sure GM is proportional to square root of W, what should happen to ID? ID must be? Okay. So that's the catch, right? I mean, if VGS minus VTH is constant, then I can say GM is proportional to W. If ID is constant, GM is proportional to square root W. If both ID and VGS minus VTH are constant, then GM is, it's basic math question, right? Nothing circuit related. So again, this again common point of confusion. So if someone asks you if GM is proportional to W or proportional to root W, what should be your question to them? What is kept constant? Okay, great. So this is GM. Let's do GDS. For GDS, I'll take this equation and differentiate it with respect to VDS. So if I do this, I'll get half mu and COX W by L times VGS minus VTH whole square times lambda. Fine. And as I already mentioned, typically the contribution of this term to the current is really small. So for practical purposes, I can say this is my operating point drain current. So I can approximate GDS as lambda times ID. So yeah, maybe I'll write it here. This is can approximate as lambda times ID. Is that okay? Great. So now let's compute the intrinsic gain here. So for calculating the intrinsic gain, I'll take GM and divide it by GDS. So let us say I take this and divide it by this. What do I get? 2 by lambda times, and of course this is obviously much greater than 1, and that's why you want to operate in saturation region. Clear? Okay, so maybe another question to you now. So I see that the intrinsic gain is much greater than 1 in saturation region but not in linear region, right? So the question is, I know the intrinsic gain depends both on GM and or not, or GDS. Which of these two parameters, GM or GDS, is impacting the most? Is the question clear? I see that the gain is really large in saturation but not in linear. I know that gain depends both on GM and GDS. The question is, which of these two parameters, GM or GDS, is getting impacted a lot when you switch from linear to saturation? GM or GDS? GM or GDS? GM. Who told GM? Why GM? I mean, look at this is the expression for GM, right? That is the power of 2. I mean, again, remember, we all started with a goal of making a 2-port nonlinear amplifier, 2-port amplifier. What should be the Y parameters for the 2-port network, small signal? Y21 is large. What about the others? 0. So now tell me, based on that understanding that, except Y21 everything must be 0, tell me if GM is impacting, or GM is impacting the gain more, or R0 is impacting the gain more? R0. Is that clear? I mean, if I go from saturation to linear, which Y parameter is getting impacted? Y22. Correct? That's how we started it. We wanted to make sure we are operating in a region where the slope is 0. My small signal Y22 or small signal GDS must be really small so that we have sufficient gain. Whereas the moment I switch from here to here, that's not the case. So what is getting changed a lot when I go from linear to saturation? GDS or the R0. So this again another point of confusion for students. Again a good interview question. Most of the time students will say, I want to operate in saturation because I get really large GM. But that's not true. You look at the expression for GM. Here I have mu1 COX W by L times VDS. Here I have mu1 COX W by L times VGS minus VTH. You can keep both of them to be roughly of the same values. Nothing changes a lot. But what will significantly get impacted is this fellow. Is that clear? That is the main reason you want to operate your transistor in saturation region and not in linear region. You always want to make sure you are operating in a region where the ID VDS has a really small slope. That's the bottom line. Is it clear? Yes. VDS will be small. So for small signals, everything is small. Yeah, VDS is small. VDS is small compared to VGS minus VTH. Okay. Okay. Remember that when I am writing the expression for GM here and I am saying it is times VDS, this is small signal VDS or large signal VDS? Large signal VDS. Okay. Because remember, all the Y parameters are computed at an operating point. We are looking at large signal picture or the operating point. When I say GM is this times VDS, this is the operating point VDS. Okay. So that's yeah.
So in saturation region of operation, so we have calculated gain and concluded that it is greater than 1.
Sure.
Sir, so how can we say that the difference of VGS minus VTH will be less than 2? Or
The idea, see, you already know, right? It is not the GM. What is impacting the most? GDS. GDS is lambda times ID. And ideally, what do you want lambda to be from this equation? Ideally, I don't want drain current to change with VDS. That's when you get zero slope. So ideally, what should be the value of lambda? Or it should be really small. So this will be really small that it becomes greater than 1. That's the catch. It is not because of this fellow. That's a very good point. This need not be greater than 1. If I didn't have this lambda, if I just had 2 by VGS minus VTH, this is not greater than 1 or cannot be always greater than 1. But because we have this lambda in the denominator, and ideally lambda is supposed to be approximately 0 or really small. That's why you get the large gain. Again, another way of saying that it is the GDS or the R0 that is impacting the gain significantly. Okay, cool. Now of course we have seen linear saturation. It turns out there is another region. What is that? Cut off. And if the transistor is cut off, which means it is not conducting, and for that the operating point VGS is less than VTH, and in this case the current is 0. So as analog designers, this is not something that you want. So the bottom line is this: a transistor essentially responds by providing a current from drain to source in response to VGS and VDS, right? So if I were to say a transistor, it provides ID in response to both VGS and VDS, and if it is operating in saturation, it responds to which voltage mostly? It should respond only to VGS, not on VDS. Okay. So which means if I take a transistor and make sure that it is operating in saturation region, and for that let's say I put some voltage here, another some voltage here. Now this is operating in saturation, which means if I change the VDS, what can you say about the current? It will not change. So looks like I'm increasing the voltage, but the current is not changing. Which other circuit element behaves this way? I have a constant current irrespective of the voltage across the device. What kind of an element is that? An ideal current source. Right? So an ideal MOSFET, which means if the MOSFET has this 0 slope, it behaves like a current source. So that's the thing, a MOSFET in saturation behaves like a current source. Okay. And if I want to change the value of this current, what should I be changing? This fellow, right? So it's not like I have a fixed current source. I have a programmable current source, and the current can be programmed by changing VGS. So it is, I can say it is a current source whose current depends on, it's a voltage. So what kind of a current source is it? A voltage control. So that's the bottom line. That's why the incremental equivalent is also this, right? Should not be surprising. That's why the small signal equivalent also is a voltage controlled current source. The current primarily depends only on VGS. And for that matter, I will say, I can argue that any transistor is a voltage controlled current source. Because historically, why did people start inventing transistors? What was the reason to start, making transistors or looking at transistors? Switch. Earlier, people used to have mechanical switches. People wanted to make electronic switches. That's when transistors came. And as you know, this is a switch. How many terminals a switch has? 2 terminals. Are you sure? You need to have this, otherwise it's useless, right? And a switch is essentially a device where an element where the current flow between 2 terminals is controlled by a different voltage. So switch, I can say it's a voltage controlled current source. So which means any transistor you make in the future will basically be a good switch. So all transistors you can model as a voltage controlled. So I'm teaching things with MOSFET now. 10 years down the line, if some other FET comes, nothing changes. For small signals, it will still be a voltage controlled current source. Okay. For the matter, I will say the entire analog circuits is basically a tail of voltage controlled current source, nothing else. Great. Okay, so now, one thing I to say, so the transistor we saw is what we call NMOS transistor, if you already didn't know. and this is the symbol we saw, gate drain source. And in an NMOS transistor, the current flows from drain to source. That's the convention we follow. And it turns out by construction, both drain and source are identical. That is, if I show a 3D cross section of a MOSFET, you can differentiate what is gate, but drain and source are sort of, you can't differentiate them. So for an NMOS transistor, since the current is flowing from drain to source, the terminal with the higher potential is what we call drain. So which means, let us say I am having an NMOS transistor. Let's say this is at 1 volt, for example. This is at 1.2 volts, 0.2 volts something. So this is at a higher terminal. So this will now be the drain, and this will be the source. Now let us say during the operation, the voltages change, and let's say this becomes 0.3 volt, and this becomes 1.4 volt or something. Then what will happen? Yeah, this becomes now the drain, because fundamentally current flows from a higher potential to a lower potential. So here is again another point of doubt students can have. So let us say look at small signals. Let's say I apply a small signal voltage V in here. There is no load connected. What will be the small signal output voltage I get? In terms of GM blah blah blah, what is it? It is GM or not, or something is missing? We just computed the intrinsic gain. How much was the intrinsic gain? GM or not, or something is missing? This minus GM or not. So that's very important. So let's say this is minus GM or not times again only small signals, right? So which means, let's say this is minus 1 volt. Let's say I get minus 10 millivolts here. So now looks like this is at minus 10 millivolt. This is at 0 volt. So do you think now the source and drain have interchanged? Already? Yeah, remember that we are only looking at small signal voltages, but the total voltage is the small signal voltage plus the operating point, bias point. That's exactly we started, right? How are we getting power amplification? This is small signal power amplification, right? From DC source we are sort of converting things, right? So just because you see minus negative voltages in small signal doesn't mean things are going negative. Just a small signal increment, you have a DC operating point on top. Great. So this is NMOS. Similarly, you have a counterpart, PMOS. Again, this is the symbol. So gate, source and drain. And in a PMOS, current flows from which terminal to which terminal? Source to drain. Which means the terminal with a higher potential will act like source or drain? Source. Again, because current flows from source to drain, source will be at a high potential. And all the current equations we saw will remain the same. So just that when we had nu n, you replace with nu p for holes. So wherever we had VGS for NMOS, you replace it with VSG. Wherever we had VDS, you replace with VSD. And the threshold voltage for NMOS, you replace it with mod of threshold voltage for PMOS, because the threshold voltage for PMOS is negative. So this is one way to quickly shift from NMOS to PMOS. Just change gate to source to gate, VDS to VSD, and threshold is basically mod of threshold. If you remember it in some other way, it's completely fine. As long as you don't get confused, it's okay. Again, remember that PMOS transistor is also a non-linear device, which means for small signals, it will again behave like How? Voltage control and in parallel with a resistor. Y22 will not be exactly 0, so a small resistance might be there. Sorry, a large resistance might be there. But a PMOS transistor responds by pumping in a current from source to drain in response to source to gate voltage. So which means if I draw gate, drain and source, so I will have current flowing from what to what? Which terminal to which terminal? Source to drain. So I have the same voltage controlled current source, but the current will be GM times VSG in parallel with. Now of course, if I say that the current flowing up is GM VSG, what is the current flowing down? Minus of GM VSG, the same as GM times VGS. Okay. So which means what can you say about the small signal circuit for NMOS and PMOS? They are identical. That should be another thing to have in mind. With respect to small signals, there is virtually no difference in having an NMOS transistor or a PMOS transistor. Only things that will change will be the values of GM or not, etc. But the model itself is still the same. So now suddenly, whatever circuits you made with NMOS, you can make with PMOS. So you know twice as many circuits as you already know. Great. So now, of course, let's get back to our discussion. Where is it? Yeah. So this is my small signal, amplifier. We now have to bias it, and for that, this is when we decided to see the IV relations and stuff. So hopefully, we are comfortable with the IV relation. And also remember that we are saying this is small signal, but we still haven't told how much is small, right? That we still haven't done. So let's do that and continue. I know I'm going to bias the transistor in which region? Linear or saturation? Saturation. So let's focus in saturation, how small the signal should be. And what is the current relation in saturation? Half mu n C OX W by L VGS minus VTH. I'll actually give some space. Yeah, okay, fine. I'll ignore the 1 plus lambda VDS. So now my question is this: in addition to my operating point VGS, there is a small change in my VGS. This will obviously result in a small change in my drain current. Now again, you have a nonlinear equation. We'll try to make sure what is the condition so that the linear term is much greater than the nonlinear term. Of course, I mean, you don't have to use Taylor series to expand because it is simple. A plus B whole square, you can expand it easily. So if I expand this, I have half mu n C OX W by L. I can think of this as A plus B whole square, right? So first I will write the square terms. So I'll have VGS minus VTH square. Similarly, I'll have half mu n C OX W by L delta VJ square, and I have 2 AB part, which is mu n C OX W by L VGS minus VTH times hopefully everyone knows A plus B whole square formula. So this is basically ID plus delta ID, and remember this is my operating point current, so basically this cancels with that. Now I have to make sure that this guy is much smaller than this. So if I do that, what is the condition I get? How much is that? I have to make sure this term is much smaller than this. So what is the resulting condition? 2 times. So as long as your small signal VGS is much smaller than twice the VGS minus VTH, and this is the operating point VGS minus VTH. As long as your small signal VGS is satisfying this condition, we are okay. So in that case, you can basically sort of ignore this term, which means my delta I is basically this. And here in particular, what is this term? That's basically G. Delta I is Gm times delta VGS, should not be surprising. 1 plus 3 is 4, 2 plus 2 is also 4, same thing. Clear? Okay.